graph theory and combinatorics, is giving this talk on the graph reconstruction problem. Over to you. Thanks. So yeah, hello everyone. Today I'm going to talk about the graph reconstruction problem with David Cole, and this problem is a pretty old one. It was posed by Stanislaw Ulam and Paul Kelly in the year of 1942, if I remember correctly. So it basically talks about whether, like, if we take the vertex-deleted subgraphs of the graph, can we determine what the graph is? So I'll just write down a few definitions which would make this more clear and more. So, like, if we have a graph G, so G of vertices, like the set of vertices being B and the set of edges being E, and then we consider GU, and okay, U belongs to B, U is a vertex to G. If we consider GU to be the graph G minus U, where G minus U means you remove the vertex U and you remove all of the edges from it. So, yeah, we consider all of these GUs and we take the set of all of the GUs. So, consider it can be a multi-set by the way. So, if I write G, this can probably be a multi-set because you can have the same graphs. Like, it's, by the way, GUs are up to isomorphism. So yeah, so you just, like, multiple GUs are up to isomorphism. So okay, you can have one subgraph which is isomorphic to another. So it doesn't matter. Yeah, we just list them down like a multi-set. Fine. So this is, we call this the deck of GU. Like a deck of cards. We call it a deck of GU. So what we do is, we call two graphs G and H hypomorphic. So if you have another graph H, so we call H hypomorphic to G, and the symbol is this. So we call it hypomorphic. If they have the same text, again, like up to isomorphism, every element is the same up to isomorphism, like occurs exactly the same number of times. In both the texts, we call the two graphs hypomorphic. Now, yeah, so like the conjecture, the problem says that if we have two graphs, G and H, so if G is hypomorphic to H, it must imply that G is isomorphic to H. So basically, hypomorphisms imply isomorphisms. This seems like a very simple problem to understand, but yeah, as I said, like, it's an open problem right now, so there's a lot of stuff that's not known about it. So today what we're going to do is we're going to talk about a lot of cases that have already been solved, and like what are the techniques that are used. So like okay, I'll define a notion over there. So we take a family of we take a class C of graphs that can be anything. Like, class means they have like one common property or something. So class just means, okay, you can have a class of regular graphs, class of disconnected graphs. Class just means a set of graphs which have some common property. So if we take a class of graph, we call it recognizable. Here, the defining property of the class can be determined from the so this means if like we're talking about Hamiltonian graphs, we can, given the deck, we can tell whether whatever graph it's coming from, is that graph Hamiltonian or not. So basically we call the class recognizable if we can determine the defining properties. Another, okay, you can also write this in the following sense. So Yeah, that's a very good question. Here we are going to talk about, okay, we're going to talk about FSU graphs. So finite, simple and undirected graphs. Simple is not an extremely important thing to keep here. There are a lot of results that I'm going to tell are valid for non-simple graphs too, where there are parallel edges and loops around. But some specific results require simplicity, and it's a bit of a hassle to deal with, so I'll just keep simplicity going. Finite, on the other hand, is necessary because there are certain proper examples known for infinite graphs. So you can, like, okay, even if you take locally finite graphs, which means every vertex has like a finite number of edges coming out of it, even those are like known to be non-reconstructible. So there are two graphs, two infinite, locally finite graphs which have the same tech, which are not isomorphic. So yeah, finite makes sense. Simple, I told you why. Undirected again, because there's something called the digraph reconstruction conjecture, which talks about whether digraphs can be reconstructed, obviously. So even that is false. So we know cases where digraphs are known to be, like two digraphs are known to have the same decks, despite being like non-isomorphic. So yeah, undirected also makes sense. Fine. So that's why we're just working with finite for a bit. Anyway, so we're going. So yeah, we were talking about recognizability. Yeah, this is recognizability, which right there, like, if G is hypomorphic to H and G belongs to C, then implies that it recognizes. Now, like, weak reconstructability is something which, if we're going to talk about weak reconstructability now. So if we like restrict our vision to a certain class of graphs, let's say C, then that class of graph is called weakly reconstructible if like any two graphs, if in that class, if they are hypomorphic, then they're isomorphic. So yeah, if H, G belongs to C, and okay, this is recognizability. H, G belongs to C, and H hypomorphic to G implies H isomorphic to G, then this is what weakly reconstructible. Yeah. So one standard technique that we use to prove a lot of these results, like not standard technique, the standard idea, is that we talk about the reconstructability of certain properties of graphs. So let's say we want to determine how many vertices that a graph has. Like given a deck, how many vertices does it have? Given a deck, how many edges does it have? Or given a deck, whether it's Hamiltonian or not, the graph that it comes from, or Eulerian or not. All of these are properties that we try to determine and then narrow down to the classes of graphs for which a certain deck. So these properties anyway, we'll move on to the properties of a graph that we can tell if we know like the tech. So, yeah. So, basic results on that. So, this is the first thing that we're going to do over here. As I mentioned, this is the non-trivial stuff that I'm going to do. Basic results, setup, and these are the kind of graphs. So, like, okay. So, given a deck, given a deck P, like if D comes from, like, okay, given a deck D, can we tell the number of vertices that the number of vertices of the graph that it comes from? That's pretty trivial. What we can do is, like if we have, like if the deck is GU, like set of all GUs after removing all of the U's. So the number of n is the number of vertices, and what we can do is we can take the number of vertices in GU plus 1. And this is true for any. You can do it with any. The number of edges, so this is vertices. Edges is the number. That too is not very hard actually, very trivial. So what you try to do is, you try to do some kind of an overcounting. So what you do is I'll just write the expression. So we know that every edge in the original graph must occur n minus 2 times if we take the sum of all of the edges of the in the graph. So this is like an overcounting argument, and then you divide by n by 2 because every edge occurs exactly n minus 2 times in this set of graphs. So edges can be determined like this. And this kind of an overcounting argument would be used very heavily. So the next thing, can we determine the connectivity? So whether the graph is connected. So yeah, this is also pretty easy because like a graph is connected if and only if its deck, if its deck has at least 2 connected elements, like it has at least 2 connected circles. That makes sense because any graph that is connected has at least 2 leaves, or if it does not have at least 2 leaves, it has at least 2 vertices which have like degree greater than 1 or something, greater than equal to 1, and then that you get that kind of result. So these connected. If G or G2 So this makes sense. This is very interesting. The next theorem is the first important one, which takes a little bit of effort to do. Not much. It's just a level. So the first part is G is disconnected. Components are reconstructed. Basically, you can just, given the deck, you can tell whatever graph it comes from, what are the components of the graph. Fine. So this, and there's another very similar theorem to this, which another very similar result related to this, which is the one that I'm going to prove. And the first result would be like an imitation of that. So the second result talks about graphs that are not two connected. So maybe one connected graphs or zero connected graphs, which is like maybe disconnected graphs or one connected graphs. So like we're going to talk about blocks of a graph. So the blocks of a graph are the maximal subgraphs of a graph which have no cut points. No cut point means, okay, removing any vertex from that subgraph would not disconnect the graph. So, yeah, I'll just write the result. If G is not connected. blocks is reconstruction. So yeah, set of blocks means okay, a block is maximum connected subgraph. There's no cut points. Cut points just means that removing that vertex disconnects the graph. So there's no cut points. No even after removing one vertex the graph would remain there. So this proof, we're going to use something called attributability of graphs. It's not something too fancy, it's a simple idea. So what we do is, we prove B and the first thing that we'll do is we'll list all of the blocks in each of the graph G. So if G are elements of the deck, the first thing that we'll do is list all blocks of all G. Now, firstly, each block of G itself must be in this listing, because we assume that the original graph was not connected. So the original graph itself is not a block. So every block must be of size n-1 or less, and which means every block of the graph would be in this listing. And additionally, there would be more blocks which would be blocks of the graphs G themselves, which should be in the graph. So if, let's say, for each block block B of G, there are n-3 copies of block matrix system. List, one copy of every block of that graph. We'll call these blocks attributable to B. Attributable. After this, what we do is pretty simple. What we do is we take the biggest graph, the biggest block in this listing. There might be multiple of them. We take one of them, and we delete all of the graphs that are attributable to that basically that graph. So if there's some block B in this listing, say this listing is L, let's say, and if B belongs to L, and if we remove all of the graphs that are attributable to B, and B is the largest, firstly, B is the largest block in L, right? So B must be a block of G also. B must be a block of G also. if we take the biggest block of this listing, it's going to be a block of G also. That's pretty trivial. Now, if it's a block of G and we remove all of the blocks attributable to this graph, and then we see the biggest block in this listing again, that would again be a block of the graph G. Right? Because if it's not a block of the graph G, then it would be something smaller than that, and then that would be a contradiction because it must come from some bigger block. Fine. So by this process, we can obtain all of the blocks of the graph after like each step. So on the first step, we get one block. The second step, we get the second block with another block. And until the list is empty, at every step we get one block, and all of these blocks form all of the blocks. I'm not writing this, but yeah, I think this is a pretty simple process. And by the way, literally the same argument would go for disconnected graphs too, because instead of blocks, you can use the word components and argue the same thing. Okay, so the next thing that we're going to talk about is, okay, we're going to talk about the circuit rank. So we know what the circuit rank of the graph is. Circuit rank is the minimum number of vertices that needs to be deleted from the graph to make it like have no cycles. So we know what circuit rank is. I'm going to write the definition and just tell you what it is. Easily constructed. By the way, like we were able to recover the fact that the components of the graph are reconstructible of a disconnected graph. That means we have proven the disconnected graphs, the reconstructibility conjecture for disconnected graphs. Because disconnected graphs, they are uniquely determined by the set of components that there is. So we have this implies the I'll write the reconstructibility for R. For this we know that it's true for disconnected graphs. That's good. Now we were on circuit rank. The circuit rank of a graph G is reconstructible. We know what circuit rank is. It's the minimum number of vertices that needs to be deleted from the graph to make it into a graph with no cycles. Now the circuit rank is a pretty simple expression. I think it's n minus n plus c or something. Correct or not? Oh, sorry. M minus n plus c. M is the edges and ends. M and n are the edges and roots. So that's its notation. M is the edges and n is the roots. This is the circuit rank because essentially we want to get to the number n minus 1, which is the number of edges in a tree, and then we want to get to something that looks like it. But yeah, the expression for the circuit rank is m minus n plus c, and we know like m is reconstructible, n is reconstructible, and c is also reconstructible by the proof over here. So circuit rank is reconstructible. This is not extremely important. The next thing that we are coming up to is going to be quite important. The clique number. So if we define the clique number by omega of c. And okay, let's say the vertex and so if we talk about the independence numbers too. Alpha dash of G. And we talk about beta of G and beta dash of G. So these are the vertex common. These are the vertex and edge independence numbers. Vertex and edge cover. Again, all of these are reconstructible. Okay, if you don't know what the vertex and edge independence numbers are, the independence number of a, like the vertex independence number is just you take the largest set of vertices in which there's no interconnection, there's no neighborhood within the set of vertices that you're taking. None of them are edges. And similarly for the edge independence number, you define it accordingly. You take the largest set of edges which have no common endpoint. And similarly, vertex and edge covering numbers are just you take the minimum set of vertices which cover the graph, which means every edge has at least one endpoint on the vertex. And for edge covering numbers, same. What you do is you take the minimum set of the minimum cardinality set of edges which have which cover the graph again. Every vertex shows up at each edge. Every vertex shows up in at least one edge of the set. So, and leaf number is this the size of the maximum leaf, the biggest leaf. Fine. These are all reconstructible. Now, reason being, okay, there's one thing that I'm going to state over here which I'm not going to do because it's not very trivial to do, but it will take some time and it's not as important to us. More relevant is this one fact. So, if we have alpha plus beta is equal to alpha dash plus beta dash. So the vertex independence number plus vertex covering number is equal to the set of the size of the vertex set. And similarly for the edge covering and edge independence number, this sum is equal to. It's sort of intuitive to see why this would be true. What you want to do is you want to keep some vertices outside which all have connections into the set that we already have, which has no connections in itself. So that's kind of like the idea. This theorem is by Galai and Mills. Maybe I'm writing spelling Mills wrong, but okay, no, that's totally it's fine. So this theorem, yeah, this is something that we know. So and okay, notice that this would be like the maximum value of the same parameter across all graphs GU in the tech. So until we have omega or alpha equaling n or alpha dash equaling n by 2, we cannot have we have the case that these would be the maximum values of the parameters inside sets GU itself. While in the case where omega equals alpha equals n, omega or alpha equals n, or in the case where alpha dash equals n by 2, it's pretty easy to conclude that reconstructibility would still follow, because what we would do is we would just establish perfect matching in some sense. So omega of G being equal to n means G is complete. Which implies that each G is complete and that is obviously reconstructible. In the case where we have alpha of G equals n, this implies that G's edge is again something that can be. By the way, I think I didn't mention something in the original statement. So the reconstruction problem is only true for vertices greater than equal to 3. So in the vertices less than 3, it's triggered to find the counter example. It's fine. So we're gonna consider only cases n greater than equal to 3. That's something that I missed. So if this implies that G is edgeless, it also implies that each G is edgeless. So again, something that we can sort of. Yeah. And the final case case where we have alpha dash G equal to 1 by 2 of n, which is a very specific case, then this would imply that G is a perfect matching. Which would again be equivalent to saying that for all s belonging to G, s belonging to vertex of G, we have G minus s as less than equal to s or no. This is, yeah, everyone knows this is the Dutch condition. Established in, I don't know, 1947 or something. Everyone knows this. This is a Dutch condition. Yeah, so this would give us reconstructibility again, because what we would have is, this would be equivalent to saying that G is no odd component. And like, okay, I think I'll just write and for all GU for all s belonging to BGU, GU minus s would have less than equal to mod s plus 1 components. That makes sense? Fine. So, yeah, that would be the case, because if it's less than equal to mod s in the first case, it would be less than equal to mod s plus 1 in the next case, because not more than one vertex would be able. That makes sense. Fine. So, I'm not erasing those over here. So, this is something that's nice. You can get these numbers and be comfortable. But there are much more specific and much more general classes of graphs which are going to be reconstructed. So we're going to come to that. This next result is going to be extremely important in the whole talk, because it's fundamental to everything that we know about graph reconstruction. It's called the Kelly's lemma. Kelly's lemma. So I'll use a notation over there. So if we have like h with h means with the vertex size less than G, then we denote n of h comma G. This denotes the number of it denotes the number of its subgraphs G isomorphic to H. And we have a similar notation like G, which is going to be the same thing for induced subgraphs. What is this? Induced. So, if we want to count the number of induced subgraphs of G that are isomorphic to H, what we're going to do with this is, we're going to count the number of subgraphs of a certain kind inside the original graph G. So, given the deck to us, we'll try to count the number of subgraphs of a certain kind that are contained in the G from which this deck graph comes from. So, this expression of the Kelly's lemma goes like ni of h comma g is equal to 1 upon n minus what we're trying to do is we're trying to count subgraphs of like count and this is for, by the way, cardinality of H, the vertex set of H less than, where n is the cardinality of the vertex set of G. Because if it's greater than that, we can't do anything about it because we originally don't know graph this constant. So this, what we're trying to do over here is count how many subgraphs of GU are isomorphic to H, and then just adding it up for all GUs. And then what we're getting is again an overcounting argument over here, because any subgraph of G that would be isomorphic to H would be of size less than equal to less than m, firstly. So it would occur in at least n minus vh many of the GUs. So every single counting is happening n minus vh many times. So a division by n minus vh would give us the exact number of induced subgraphs of G that are isomorphic to H. So this seems like this is something very okay, fine, not very good. What will we get out of this? But immediately we can figure more stuff out about the graph that we have. Let's say we can figure out, let's say, degree of every vertex. There's one thing that we can do. So the first thing, okay, by the way, this from here it's clear that ni of h comma g and n of h comma g are reconstructible. So these two numbers can be constructed back from the deck if we have a deck. Fine. So these two numbers are reconstructible. Now, one thing that we can immediately get out of this is, let's say, okay, we had this assumption of simplicity anyway, but we are right here, because up till here all of the results were not specific to simple graphs. So G is simple. G is simple, then what happens is, what we can reconstruct is the degree of each U, i.e. dg of U, each vertex U, and the second thing that we can reconstruct is the cardinality of the edge set of the neighborhood of for each U. So if we see the edge set of the induced subgraph of the neighborhood of U, and then we see its cardinality, we can reconstruct that. And another thing that we can reconstruct is the degree of the neighborhood. So these three are stuff that can be reconstructed using the Kelly's lemma that we have. So degree of U for any vertex. So if we want to get the degree of U, what we can do is this can be expressed to form degree of like the number of edges in G minus the number of edges G. Minus number of edges in G. So this is the degree of U. And how do we get this? We can get this by comparing K2 to G. So what we can do is we can take the number of isomorphic subsets of G to K2. So K2 is just an edge in some sense. So we are trying to count the number of edges in G. So give us the DG Q is equal to, let's write this. This is equal to And the nice thing is we have this expression over here which is reconstructible by the Cartesian lemma, due to which we are being able to do this. So, yes. We will do a similar thing for the second expression, which is the cardinality of the H set of the induced subgraph generated by induced subgraph of the neighborhood of U. So if we have the induced subgraph of the neighborhood of U, and we see its cardinality, so this will look like so this is equal to, okay, so like what is this number? This number just tells us the number of triangles in which, like the number of triangles in G which contain it. So this would look something like K3, G minus K3, G. Yeah, this gives us this number. And the extrapolation of this will tell us that if we have two graphs which are hypermorphic, they would have to have the same like given a subgraph H of G and H of, let's say, K. If G and K are isomorphic, then both of them would have to have the same number of subgraphs of every kind. So if we talk about, let's say, a Peterson graph, if G contains a Peterson graph in like n different ways, then K would also have to contain the Peterson graph in k different ways, in k different cases. So yeah, that is one thing that is applied by the Cartesian. And that's pretty nice because that gives us a very huge restriction to the set of graphs which can be in like the hypermorphism classes. So yeah. So another result that we have over here is, what did we state over there? Yeah, degrees of the neighborhood. Degrees of the neighborhood. Okay, for this you will do one small trick. It's very simple. What you do is you take the degrees of the all of the vertices of G except U. So if we have D1 less than equal to D2 less than remember, these degrees are reconstructible by what we said before. So these are the degrees, and then now we consider the degrees of all of the vertices in G. So this is inside G. This is in G. Now we consider the same thing in G. So if we do this, G2 dash. This is in G. What would happen is we can obtain the degrees of the neighbors of U by specifically choosing those degrees which have decreased by. So what we do is we take the subsequence of this, which looks like di. So that di dash is less than di, strictly less than di. This means that di is a di, which means that I is a neighbor of the original vertex U, and now we get the degree of each of the neighbors. That's fine. Now, the next thing that we're going to do is something that's not going to make a lot of sense, but the goal I'll make clear. So whatever you're going to do after that is a build-up towards proving that all Hamiltonian graphs are recognizable. So recognizability of Hamiltonian graphs is we can given a deck of some graph, we can tell whether the original graph is Hamiltonian. So turns out it's quite a task and we have to do a lot of work for that. But before that, whatever we proved over here, whatever we did over here gives us as a corollary that Eulerian graphs regular graphs are reconstructed. This is pretty easy to see because for Eulerian graphs, what we can do is we can argue that in the original, like in the deck that we have, if we realize that the degree of V minus degree of U is not degree of W is not equal to 1 at any point of time, the graph is Eulerian. So yeah, and for the regular graphs we can do the same. So implies that for all V implies that G because yeah, in like regular graphs or Eulerian graphs are reconstructible in this sense because we can get the degrees of each of the vertices and then we can get degrees of each of their neighbors and that will now we have to fact that Eulerian graphs and regular graphs are reconstructible. That is a big thing, that's nice. But our aim over here now is to prove that Hamiltonian graphs are recognizable. So and spell down the E now. E over here is now we're going to build a bit of theory from that. I will stop this. So we know what spanning subgraphs are. Spanning subgraphs are the subgraphs which contain all of the vertices of the graph. There might be isolated vertices in the graph, that does not matter to us, but it just needs to contain all of the vertices in the vertex. So spanning subgraphs. And this technique that we're going to write down was again developed by W. Theta in this paper published in 1979. The first thing that we'll do is we'll define something called realization of a sequence of k-graphs. So if we have a sequence of k-graphs, it's just sequence just means a set of k-graphs. There's nothing very sequence-like in that graph, in that set. Sequence k-graphs S equals x1 up to xk. So this is the sequence of k-graphs, and I will write on. this sequence is present in the graph in some sense. And a carrier of realization is G. I might frame it like this. G is H1, the union of Hi over I. So basically, like the subgraph which contains all of the subgraph of G, which is H, which contains all of the HI's perfectly inside. So this is called the carrier of realization. And we're defining this to just like count the number of subgraphs of certain kinds again in the version. So we'll define something called delta of S comma H, which is it denotes number of realization of S in H. Whose carrier is it? Whose carrier is H? Carrier is H. Okay. And script H or something, I don't know how to put it in this. Script H. Let script H denote the set of all powers. Now we're going to look at this sum over all H. This H is not the script H by the way, so this can be some other set, which is a subset of script H generally when you're going to talk about it, over some set of like graphs of del S over H. So in some sense, we want to count all of the realizations of the set S inside the graph G. And yeah, all different kinds of sizes of subgraphs of G which would provide us realizations of the original set S. So his notation is necessary for whatever we do now. So sigma naught just represents a sum of this sum over all H in the script H, this sigma VP represents some on H belonging to H such that cardinality of VH is less than N. This notation, I guess everybody knows now. I'm doing the top part. It's unnecessary. So this is something that is going to be important. So I'm not talking this. And then we have sigma. So this is VP. Again, denotes the sum over all H belonging to H such that the vertex set of H is cardinality is set. Then third one is sigma S, and then sum over all H belonging to H such that cardinality of H equals cardinality of vectors equals cardinality of the vertex set of H is equal to N, and this sigma SD, which is sum over all H belonging to H such that the vertex set of H has cardinality N and the set is discrete. H is and then this something that we have sigma SC. So if SD we have disconnected, then for SC we have connected. This is like the complement of SD in the set of sigma S. So it's like sum over all H belongs to H such that the vertex set of H has cardinality N and the set itself is connected. So what we'll try to do is argue that each of these numbers themselves are reconstructed, and then we'll argue something regarding the Hamilton terms. We'll argue that these are reconstructed. So for the first one, it's not very hard. So the first one is sigma, which was what? It was the sum over all H belonging to H. So vertices can be less than n2, equal to n, less than n1. So sigma naught is the sum over that. So by the way, all of these are sums over this number. So I left a blank H over here because you can fill in with sigma naught, sigma will be whatever you want in the context of what we're doing. So sigma naught is a sum of this over all H belonging to H. So this, if you notice, is just the total number of realizations of H in, sorry, S in G. So how do we get the total number of realizations of H in G, S in G? Because okay, what we can do is we can take elements of S which are x1, x2, x3, xn, or xk, xk. So and then we can take the product of all of the numbers of subsets of G, like subgraphs of G, which are isomorphic to xi. So we had this expression that we knew that looked like n of xi over G. This was the number of subgraphs isomorphic to xi in G, and we knew this was reconstructible. We proved it a while ago. So then we can take the product over all these, over all I, and this would give us sigma 1. And then we have like the second case where we have sigma VP. So by like Kelly's lemma, sigma VP is also reconstructible. Sigma VP is reconstructible by Kelly's lemma. So sigma VP is fine. We will go and it's reconstructible for vertices less than n. And okay, if we have sigma VP and sigma naught, what we can do is we can get sigma S by subtracting sigma VP from sigma. So S is the case where we have exactly n vertices. So by the way, all of this we are doing to cover up for the case of n vertices. Right now, Kelly lemma only tells us about vertices less than n. So we want to say something about something about graphs, like subgraphs of G that are like isomorphic to components of like bigger graphs which have the same cardinality. So yeah, so what we can do is we can take sigma S to be equal to sigma naught minus sigma V. This gives us the reconstructibility of these three numbers. Sigma naught was reconstructible, sigma VT was reconstructible, reconstructible by installation. Okay. Now what's left is sigma SC and sigma SD, which is the case of sigma S where the graphs are disconnected and connected respectively. So if we have something, if we have for sigma SD and sigma SC, what we're going to do is we're going to state another result which is going to prove the reconstructibility of these two numbers. So this other result is k that is connected. Its cardinality is what? Equal to n. Like the subcardinality of the subgraph k is equal to n. So if we have the cardinality of the vertex set of k equal to then nk comma g is reconstructible. That's what we want. So this is a result that is basically an extension of the Kelly's lemma for certain kinds of graphs which have vertices more than n, which is vertices equal to n in this case, and we try to establish a Kelly lemma-like result over here for disconnected graphs of cardinality. So yeah, we are going to prove it using realizations again. So S is x1 x k. And x1, x2, xk are components of k, which is the disconnected graph that we have. So x1, x2, xk components of k. And okay, what can happen is in the components there can be certain isomorphism classes of components. So there can be certain components in the graph that are isomorphic to each other. So we're going to just compartmentalize them into separate isomorphism classes. So if we have the isomorphism class of cardinality k1, k2, k3 and so on. So it's kr, k sum would be equal to sum is going to be equal to what k, right? Because there are k many components and so on and so on. Okay, if H is a spanning subgraph of G, so H spanning subgraph of G. What we want to see is we know that cardinality of H is equals to cardinality of vertex set of H is equals to cardinality of vertex K, because okay, we're doing this for disconnected graphs of cardinality exactly equal to the original graph that we had. So this is going to be okay again. Yeah, this was equal to by the way summation of the cardinalities dx. Okay, there are two cases that we're going to handle over here. The first case is going to be where H is isomorphic to K. That's pretty simple. What we do is if H is isomorphic to K, then like we would compute what delta S comma H is. So delta S. So the first case is this. So delta S comma H would look something like summation Ki factorial. Ki factorial for all I equal to 1 to 1. This is Ki factorial because for the specific isomorphism classes, you can permute them in I many ways for each of the isomorphism classes. So, like for the first isomorphism class, it's going to be permuted in I many ways, Ki many ways. For the second one, again Ki many ways, which would give us something that's like K1 factorial into K2 factorial and then K3 factorial. So this would be this expression was. And like this is the case, and the second case is again it's second case is also completely different because if H is not isomorphic to K, then what would happen is delta S comma H would become 0, right? Because we are dealing with disconnected graphs. So this is going to become 0, and okay, so for non-isomorphic, like H not isomorphic to K, we get that delta S comma H is 0, and for the other case we have delta S comma H being summation Ki factorial. This gives us the result that okay, n key from the G would be this is going to be equal to okay, we have an overfunction argument over here again. We go to all. I wrote some over here, right? It's wrong. So yeah, product of all of Ki factorial into summation every element in there is being counted the product of Ki many times, Ki factorial many times. So get this to get n kg means divided by the product of Ki factorial, which gives us the exact number of times every element of n k comma g by every subgraph of g which is isomorphic. It's counted. So we have something over here, fine. Okay, this yields the reconstructibility of since each of the KIs are reconstructible because the components are reconstructible. So is use the reconstructibility of the image. The reconstructibility of nk comma g. If nk comma g is reconstructible, the original statement is proven, right? Which is basically, that is what we wanted to state. And if nk comma g is reconstructible, that immediately yields us that sigma of st is reconstructible, right? Because that's essentially what sigma of st was. We were taking some over all h which were disconnected and had cardinality in. So we just got this expression right there. And if we plug that into this expression, we're immediately going to get the expression for sigma s comma d. And as soon as we get an expression for sigma s comma d, we're going to get an expression for, so if we get an expression for sigma s comma d is what? If we have we want sigma sc, right? Sigma where like cardinality is n and every one of the graphs, like the graph is connected. So get that and state the component in the set of sigma s minus subgraph st. So just after that, sigma sc is also reconstructed. So yeah, so this gives us the reconstructibility of all of the numbers that we defined over here. And what we do after this is we try to find the non-separable subgraphs. So, like, how do we say it? If we want to denote the subgraph, like the spanning subgraphs of G with Q many edges, what we do is, okay, if it's NQ and we want to see the connected non-separable graphs in it, what would a Hamiltonian cycle in a graph G look like? A Hamiltonian cycle is, okay, you know what separable means, right? No. So I'll just discuss it quickly. I'll just double it once and then discuss it. We define, okay, before that what we would like to do is we would also like to state a theorem which is basically the repetition of this argument in a different context. So the argument that we gave here for figuring out nk comma g, using the reconstructibility of nk comma g. So this here is something like so if I have then if these are blocks of a second graph, so it doesn't matter what class they come from, blocks are just as we know here it's maximal two connected subgraphs of some big graph. They're just maximal if they're connected and removing any vertex from the ring is just another there are so if x1 to xk are blocks and then the numbers n comma n of c which are subgraphs, number of subgraphs These are subgraphs of G, by the way, which we are discussing. Those K blocks. K blocks are isomorphic. To exponential scale. These numbers are so I'm not writing a proof for this, but the proof follows along the lines of the previous proof. There's a bit more technicality in that, and I know I'm running short of time over here, so I'm not stating this proof right now. But please note statement for believe it. It's quite sense. It makes a lot of sense too, because we did this for disconnected graphs with their components. So instead of components, we have blocks over here, and we're trying to do the same thing with blocks. So the arguments follows right away. There's a bit more that I'm going to define over here, which is required for the Hamiltonian part of the graph, which is this is for the ease of notation, like ease of notations that we have over there, so that like we are not confused about what we're talking about. So here NQ denotes the number of spanning subgraphs of G. Q is. For and DQ, one can understand from the D that it's about the disconnected spanning subgraphs. And CQ is just the complement of that in this set of basically, if we consider a set of which we are taking the cardinalities, then it's just a complement of this set and DQ. So connected subgraphs. And CSQ is for connected and separate. So separable just means okay, it's not to connect. So remove there exists one vertex that you can remove from the graph, so that the graph does not remain connected anymore. So this is connected and non-separable. Which means every basically you can't disconnect the graph by removing any one vertex. It's too connected. That's what it means. So these two are complementary. And this NC and Q is what's going to yield us Hamiltonicity of a graph given the deck. Because we want to, because Hamiltonian cycles in the graph and Hamiltonian circuits in the graph are basically connected non-separable subgraphs, and we're using Q over here, so we will see what we're trying to do. So we are claiming that these numbers are deconstructible. So these are deconstructible. So the claim is pretty simple for a few of them, not so simple for the others, but yeah. Okay, this still not one. NQ it's pretty simple because that's just a number of subgraphs of G which have Q many edges. So that's just H set of V, H set of G. Choose Q. So we're just choosing Q many edges. So C this is equal to the card and Q set of G. Choose Q. This is the reconstruction. This is equal. Next number is NCQ. Okay, NCQ is something that we're gonna prove to be reconstructed by proving NDQ, which would give us NCQ is equals to NQ minus NDQ. So for NDQ, we need to prove that NDQ is reconstructed. So note that NDQ is equal to summation NH comma G for all H, where H belongs to the set of all disconnected non-isomorphic graphs of cardinality n. So, and yeah, every single one of those have Q many edges. So, but this is something that we calculate here, right? So this is something that we get directly from sigma ST. So yeah, this we get from the set of like realizations in G of S. So that gives us the set of all non-isomorphic discrete graphs of HSQ and vertices. So yeah, so what I'm claiming is this is reconstructible from the fact that sigma SD itself is reconstructible. And since we have disconnected graphs of like with n many vertices, for each of them we know that NH comma G is reconstructible because we proved it somewhere that N K comma it's a theorem that we proved and K comma G is reconstructible, which immediately gives us the result that NC Q is equals to NQ minus ND of Q is reconstructible. And now for the other case, we stated this theorem for the other case, which was NCS and NCN. So that NCS is equal to summation over H of NH comma G. What kind of graphs are H? The sum is over the connected graphs of H, which the connected subgraphs of H which have at least two blocks. So, like this theorem was about it was about number of subgraphs. Like number of subgraphs and number of connected subgraphs whose K blocks are isomorphic to x1, x1, x2 up to xn. So what we're doing is we're taking subgraphs of yeah. So what we're doing is like we're taking a set of all non-isomorphic connected graphs which have at least two components and have exactly q many edges and n many vertices. So that set was right here, like that was NC, right? So we have NC over here, and NC would allow us to start over here, and yeah, it would give us the result for NCS, and this would we would have an SD or DS, whatever we wrote, being equal to n q minus n. NCQ minus NSC. Fine. So this would give us the reconstructability of all of the numbers that we had over there. And now we are ready to state that we can reconstruct the Hamiltonian city of the graph. So if we have a circle, right? And we immediately get this because this number is nothing but equal to NCN of n. So we want to see subgraphs with n many vertices, and okay, so we want to see subgraphs with n many vertices which are connected in non-subgraphs. So what subgraphs can have n many vertices, n many edges, and are connected in non-subgraphs? They're exactly Hamiltonian cycles. So I'll repeat it again. Only Hamiltonian cycles are subgraphs of a graph which have exactly n many vertices, which is the number of vertices of the graph. They're connected and they're non-subgraphs. So if you have some Hamiltonian cycle that looks like this, it firstly contains all of the vertices of the graph, n many, it's connected, and it's non-subgraphs, which is it's two connected. So removing any vertex would still give us a connected graph. So since we proved that NCQ is reconstructible, NCNQ is reconstructible. Basically, we can determine NCNQ from the original graph. This means we can determine NCNN from the original, like from the deck, and then we can state that Hamilton is Hamilton is I guess this is not much time for me. I'll state one more very nice theorem. And after that, so we want to do some spectral result about the characteristic polynomial of the graph and ask whether it's deconstructible or not. So if we have some graph G and we have its characteristic polynomial, so if the characteristic polynomial looks something like x bar n plus n minus 1 x bar n minus 1 up till a naught x. This is the characteristic polynomial of the whatever it is. This is the characteristic polynomial. If we write it in the form of eigenvalues, x minus lambda 1 minus lambda 2 x minus lambda n. So these are the eigenvalues of the adjacency matrix. All of them would be there because the adjacency matrix always is eigenvalue. It's symmetric. So what we need to do is we just need to prove that AI's are equal. But okay, if I write the expression of the AI's in terms of the eigenvalues, so every single AI can be expressed as some polynomial of the eigenvalues, right? So if we have a n minus 1, it's going to be equal to minus summation of ai. Not ai, lambda, which is basically in some sense the trace, kind of. And for an minus 2, let's say, this would look something like, okay, so I'll like give a notation over there. Sigma k just means summation of lambda I raised by. So if an minus 2, this looks like half of sigma 1 square minus sigma 2, and so on. So every single coefficient of this polynomial can be expressed in the form of this these sigmas. All we need to do is prove that these sigmas are reconstructible. So what do these sigmas represent? So sigma k is just the trace of, if the adjacency matrix is A, so it's just the trace of A per k array. Now, what does the trace of A per k signify? It signifies the number of closed walks with length less than equal to k. So, not less than equal to k actually. For k, it represents the number of closed walks with length equal to k. Now, basically any walk with length k, when k is less than equal, okay, if it's less than n, that walk must appear at least in at least one of those like GUs, one of the elements of the deck. And if it's greater than like k, like if it's equal to n, if the length of the walk is equal to n, so it might be a Hamiltonian cycle. But we realize that we just proved that Hamiltonian cycles are reconstructed, or Hamiltonicity of a graph is reconstructed, or the number of Hamiltonian cycles in a graph is reconstructed. So all that we need to do is we need to figure out the number of closed walks of length k in the graph, which is again something that's reconstructible, because we know that the Hamiltonian cycles are reconstructible, the number of Hamiltonian cycles and the number of closed walks are reconstructible within a single G. And a sum over that, and again an overcounting argument that looks like Kelly's lemma or something would give us basically would give us the sigma lambda is raised by k. And this would indeed give us the characteristic polynomial of the instance, which means the characteristic polynomial of a graph is reconstructible, which means all of the spectral properties of a graph are reconstructible. That's something that is known. I think I've run out of time. I just wanted to state something about the edge reconstruction conjecture, which is a sort of a weaker version of the conjecture that we have here. And I had a few theorems that I wanted to state, but I guess I won't be able to. A couple of them, but yeah, just the fact that it's the edge reconstruction conjecture, which basically talks about the edge-deleted subgraph. So whether given the edge-deleted deck of a graph, basically deleting one edge at a time of the graph and taking the deck, whether from that we can determine the original graph. This is something that's implied by the vertex reconstruction conjecture. Yeah, the proof was very nice, but yeah, I think it's a very simple proof. You can look it up.